Hello, everyone. Welcome to what I think many of you know is a truly historic day for science, for astronomy, for really human ingenuity and the passion to explore. You know, our programming here at the World Science Festival is under the banner of Big Ideas, the Big Ideas series. What we're talking about today is among the really biggest ideas because it spans not only trying to understand the cosmos, but to explore the cosmos, to observe the cosmos, to measure the cosmos in ways that we have never done before. Of course, I'm talking about the James Webb Space Telescope. You may recall that it launched back on Christmas Day, 2021, traveled around 1 million miles out into space to the L2 point, the second Lagrange point, for those of you who remember your classical mechanics, then spent a nice period of time unfurling the sunshade that will protect the delicate imagery, unfolding the 21-foot mirror with these 18 hexagonal pieces fitted together like a jigsaw puzzle, and then began observing the cosmos. And today, the first images from the James Webb Space Telescope were released, and we're going to have a discussion with some of the key people responsible for this amazing technological scientific feat. We're going to have a conversation about those images, what they tell us both about the capacity of the telescope, as well as the insights that perhaps we are going to gain in the next weeks, months, years, and as it turns out, even decades. So joining me first for this conversation is someone who's familiar to many of you. He's been on many of our World Science Festival programs in the past. I'm referring, of course, to Nobel Prize winner and senior project scientist for the James Webb Space Telescope, John Mather. So, John, welcome to the conversation.
My goodness, thank you for having us.
Yeah, no, I can't imagine what it must feel like. I mean, you've been at this for what, 25 years, maybe?
Actually, more. It feels like a tremendous relief because something that was really pretty scary worked out very well in the end. And very exciting to see the possibilities coming because we never knew what this telescope would actually show us until we did it. So we just finished setting it up on Sunday.
So can you just take us through that? We're going to bring in a number of your colleagues in just a moment to go through some of the images that were released today. But can you just set the scene for us? I briefly went through the history, but, you know, so from launch until today, what's been happening?
Well, it took us, as you said, 2 weeks to unfold the telescope. Then it took us another almost 4 months to finish setting up the telescope itself, and then another 2 months to finish setting up the instruments. So we know how to focus them all, how to set up the exposure times, all the things you have to do with a very complicated digital camera. So there it is out in space, and it's got all these filters to choose and the exposure calculator and all those things. We have to verify that it's really in focus. So we did that, and now we are sure it's working.
And were there moments when you metaphorically or literally were holding your breath because if such and such didn't happen, it was over? Is that the kind of situation that you faced?
Well, of course it is, but I'm not good at holding my breath. So I'm take it as it comes. You know, we built it, we did everything we could to make it work, and as it turned out, everything worked. We didn't have to go to the backup plan for anything. So
Really?
It's a testament to the brilliant engineering that we did and the brilliant people that made that possible.
What about that we heard? Certainly, I didn't follow it in detail because it turned out, I gathered, to not be a big deal, but a little space pellet rock, something hit one of the mirrors?
It did indeed. We've actually had about 6 of them. Only one was really noticeable, but even that one was about a thousandth of an inch across. If you had it in your fingers, you'd never know. But it travels at maybe 30,000 kilometers, 30 kilometers a second. You know, that's fast enough to hurt. So it did actually make a little dent. and it's okay.
But it's okay. All right.
Yep.
Well, great. And so before I bring in four of your colleagues to discuss some of the images in detail, and of course, I'd love to hear your detailed comments on those images as well. But overall, I mean, are you over the moon with, maybe that's not the right metaphor, I should say,
over the
Hubble
galaxy.
telescope or over the L2 point, whatever the right metaphor is.
Over
I mean,
the whole galaxy. So
yeah.
we have done what we said we would do. It was incredibly difficult. It took forever. It involved all our international partners and huge aerospace companies. So a teamwork of 20,000 people to put this thing together and make it go.
20,000.
20,000 people. So our project manager, Bill Oakes at Goddard Space Flight Center, made that happen. So we were thrilled that he did that. And you're going to meet the people that made this happen, building up the instruments that are in the telescope or attached to the telescope. I think it's maybe worthwhile saying we all had history before we got to this. As was mentioned, I worked on the COBE satellite. At the same time we were building that, my friendly competitors were stealing the best engineers to work on the Hubble Space Telescope. And people were already planning the Spitzer Space Telescope. So at least two of us worked on the Spitzer as well. So
wow. Yeah.
When it came time to think about what are we going to do next after the Hubble, there was already a conference before Hubble's launched that said, this is what we think we need to do. After we got the Hubble fixed, a committee wrote a book that said, please build us this. And we did what they said.
Yeah. It's amazing. It's amazing.
It's a brilliant book. It gives you goosebumps to read it.
Yeah. I'll have to check it out. But that really is just an amazing, even summary story of an incredible achievement. So let me bring in some of the folks that you just made reference to. Pierre Farouet, George, and Marcia Ricci, they've spent, I gather, almost as much time devoted to the Webb telescope as you have. Maybe not quite as many years, but certainly have devoted significant part of their professional lives over the past couple of decades, leading the development of a number of the key scientific instruments that make the Webb telescope what it is. So more specifically, Marcia is the principal investigator for the near-infrared camera known as NIRCam, which produced the stunning deep space image that many of us saw President Biden react to, unveil yesterday, which certainly was a fun moment. Pierre is the European Space Agency's project scientist for the near-infrared spectrograph known as NIRSpec, which is using innovative technology to help scientists find the earliest galaxies in the universe. And George is the science team lead for the mid-infrared instrument known as MIRI, which measures infrared wavelengths that are beyond the scope of either NIRCam or NIRSpec, as no doubt we will hear as we go forward. So I'd like to welcome them to our discussion. We also may have Rene. We do have everybody. Fantastic. I wasn't sure if Rene Bayon was here, but he's the principal investigator for Canada's contribution to the Webb telescope, which can be thought of in some sense as a twofer. It's a fine guidance system and also a near-infrared imager and slitless spectrograph known as NIRISS. So let's jump right in. First of all, thank you all for taking time out for what must be an incredibly busy day to have an exploration and conversation about the images that were released. I'd like to begin with the deep space image that President Biden saw yesterday, and it's quite touching yesterday to see President Biden almost like a little kid, just so excited by all of the ideas that are embodied in this image. So, Marcia, let's begin with you, because I think NIRCam, your instrument, played certainly a key role in fashioning this image. Can you tell us what we're seeing here and how you go about extracting the data that allows an image like this to be shown to the world?
Okay, what you're seeing is a NIRCam image that's comprised of 6 different colors. NIRCam can measure 2 colors at once, so it took 3 different exposure settings to get these 6 colors. And you can see, if you look closely, there are some objects that are very red and then some that look much bluer. You will also see some objects just a little bit right of center that look kind of like little arcs. what we're seeing is a galaxy cluster that's about 4 billion light years away. In other words, we're seeing some whitish, fuzzy, elliptical shaped galaxies at the center that are the star cluster that is far enough away that the Earth was hardly formed. And it has the effect of its gravitational field bending light, so we get these funny arc-like things that are actually background galaxies. Elsewhere in the image, you can see little smudges that are very distant galaxies. And when you have these 6 colors from NIRCam, what you can do is make some what I would call guesstimates of how far away they are by the distribution of the colors. And one of the ways that Pierre and I have our teams have come together to use Webb for a project that will be done in September is to take an image like this, figure out from the colors which are likely to be the most interesting distant galaxies, and then use NIRSpec to take spectra of them, which is exactly what was done with this image as well. So we're seeing, as far as I can estimate, not all the way back to the Big Bang, but within a few 100 million years. And we're hoping in September that we'll get within maybe 50 million years.
And so Einstein would certainly be thrilled by those arcs, no doubt, something that comes right out. I mean, any of us who teach the general theory of relativity, we teach this to our students, and, to see it right there in the imagery is really quite stunning. But you made reference to Pierre's work in NIRSpec. So Pierre, can you tell us, I mean, I think our audience probably already knows, but quickly, what does it mean to do spectroscopy? What does that word mean in this context? And then what do you do with sort of an image of that sort to take the analysis even further? And perhaps image on our team, image 17 might be a good one to bring up when Pierre is describing this.
I think trying to explain first, in fact, it's a NIRISS image, this one, a NIRISS image and accompanied by a NIRISS spectra. So to explain, basically, when you take an image, Marcia told about these different filters. So you look at different colors. Spectroscopy, you push it further. You break down in colors, but in very large number of small color amounts, basically from a few hundreds to thousands. And you create a spectrum. And it's very similar to what happens, when raindrops split the light of our sun into a rainbow. Basically, a rainbow is a spectrum of our sun. So both NIRISS and NIRSpec, they are more sophisticated than raindrops, much more accurate also. So they use what we call grism or prisms or gratings to split the light in its colors, and you get these spectra. So then the game is really to look at, which amount of light do you get in any color? We call them wavelengths. So on these diagrams, this is the x-axis wavelength. And what you see here is that at some wavelengths, at some colors, you get actually a spike of light, more light. And it's actually the fingerprint of some elements, in this case, the oxygen and hydrogen. And we know where these lines are expected. These lines, they are expected. And depending on where we observe them, we can actually figure out how this galaxy moves away from us, in this case, and in fact, from that, get their distances. And this example is striking because you were talking about Einstein and the gravitational lensing. Here you have two, in the small squares, you can see two distorted galaxies, some arcs, which are actually two images of the same galaxy. We think it's the same galaxies. And when you look at the spectra from NIRISS, you look at them and you find that indeed these lines, they fall exactly at the same place as the same wavelength, really giving us a strong proof that this is the same galaxy. They don't have to have the same amount of light, because when they get lens, they get magnified differently. So one may be brighter than the other, but really the telltale sign is the position of these lines. And spectroscopy, as you can see, brings additional information about what is inside this galaxy. So that's kind
hugely
of
powerful. Yeah.
Yeah.
That's wonderful. So Renee, so NIRISS is a instrument that is close to your heart. Can you take us even a little bit further into what we're seeing and how does the way in which your instrument takes spectrum, how does that differ from, say, NIRSpec? So there's two of these spectrum instruments. How do they differ?
Okay, so the image you just shown, that was an image from in fact some spectroscopy data from NIRISS. So this is one of the 4 observing modes from NIRISS. So in this mode we can take spectra everything everywhere in the scene. Now NIRSpec does it by taking little slitlets, by selecting the object. That's the NIRSpec data here. And in fact, to do spectroscopy, that's the way to do it. You really want to isolate your objects from any background contaminations from other sources, even the sky. The sky background is bright, and you want to avoid these contaminations. Now, so NIRSpec can take a few hundred objects at the same time. Now, in NIRISS, we don't have any slits, so we take spectra of everything in the scene. Now, you do it with less sensitivity, but instead of looking at a few hundred objects, you're looking at maybe thousands of objects at the same time. So it's very complementary to NIRSpec to do spectroscopy, and Pierre, and so it's a way to actually find candidate high redshift object, very distant objects, and then tell NIRSpec and maybe, look, that's an object of interest, so you should put your slit on it to get a much more detail. So you have a very good example here. This one that has show oxygen, but much better the definitions. It's an object that has a look back time of 13.1 billion years. So that's one of the observing mode. And what I like of this image of the deep field is that it was observed at all 4 science instruments. It just shows how the 4 science instruments are complementary with one another to do one common science team. In this case, study the most distant galaxies in the universe.
So let's bring in the 4th instrument if we could. So George, you're dealing with wavelengths that are a little bit different than the others. Can you tell us, well, in fact, why don't you even tell us why infrared? We haven't actually said that, so that might be a good thing. And why the particular range of wavelengths that MIRI focuses upon?
So I'm representing the mid-infrared instrument that starts at 5 microns. That's about 10 times longer wavelength than visible light, and goes out to about 25 microns. And that is a very difficult wavelength range to observe from the ground, because that's where the infrared emission of the atmosphere and your telescope just swamped the detector. And in fact, we learned how to detect sources that were maybe 100,000th of the total flux coming onto the detector. That in itself was miraculous. That gave us hints of what to look at. That's where you look for planets, for example. Planets are right at the temperature that glows bright to the mid-infrared instrument. It's where you look for forming stars, because the material that's falling into the forming stars warms up to exactly that kind of temperature. So it kind of opens up your sight to a whole new set of phenomena. It's not dominated by stars, and the stellar emission is dominated by other things. And that's what's so exciting looking with Webb, that it's above the atmosphere, so it's cooled down, so all of this emission goes away, and it's big. Big is incredibly important, because the sharpness of your image depends on how big your telescope is. And so the resolution element of Webb is 1/50th the resolution element of the best previous cold telescope we had in space. Think of it, it's like going from 20 megapixels, it's like going from half a megapixel up to 20 megapixels with your camera, to give you an analogy.
Yeah.
And so we're just seeing things we never saw before at this wavelength region. And that's what's going to be so excited. I guess I could add, at the beginning, MIRI was kind of an optional extra on JWST. It wasn't one of the regular instruments.
I heard you had to argue for it.
Oh,
right?
We had to argue for 5 or 6 years.
Oh, that's quite an argument.
It was a long-standing argument, but 10 European countries stepped forward and made contributions. NASA eventually decided to buy the optional extra, And the early release observations show what a smart decision that was, because it's opened up this whole set of new phenomena that you just don't see with the other instruments.
Yeah. So jumping off from that, John, there's this image that I'm sure it's everyone has seen it. I think we have it, which kind of does a comparison, because you mentioned various other projects and telescopes that you've worked on. Can we see that image number 20 that just gives a sense of the resolution change? Not this one, image number 20. Yeah, thank you, that one right there. So yeah. Tell us what we're seeing here.
Yeah, so this is a comparison of 3 telescopes we've had in space. The WISE telescope is a small one, sort of the mirror is about big as your hand, a little bit bigger. The Spitzer telescope is quite a bit bigger and much more sensitive, and it showed us that even though it was small, you could see pretty far, galaxies pretty darn close to the Big Bang, not all the way. And then you see in the right-hand picture, the area of the same thing is so much sharper and so much clearer, and it reveals features that are now obvious that weren't so obvious before, which are dust clouds in space. Not only are there stars, but there are these wispy things out there which are really important to our story of where do stars come from. Because stars get old and they blow up and stuff comes out and it gets recycled into clouds like that, which will then get pulled together by gravity to form the next generation of stars with planets. So this is why this is such an important story to look into and to begin to tell.
Yeah, I mean, one telescope that's not listed there, but I think is probably the most familiar to those in the audience, is the Hubble Space Telescope. Maybe just to give a sense, like, what's the size of the mirror of Hubble compared to the size of the mirror of the James Webb?
Okay, well, Hubble mirror is 2.4 meters across, is about 8 feet, and the Webb is 6.5 meters across, almost 21 feet. So it's about 7 times the collecting area, but you can see what a spectacular difference that makes.
Yeah, no,
So-
it's quite impressive. Yeah, please.
Also, the Hubble can't see at these long wavelengths that are in this picture. It can't see at all because it's warm,
Right.
and it glows like a light bulb.
Yeah, the Spitzer telescope, the middle one in that picture, was 3 feet. And that was the most sensitive telescope that we've had at these wavelengths. And so you go from 3 to 21 feet, and you actually go as the square of that ratio. That's how you get the 50 times sharper image. And this picture makes it show that you're just seeing things you never saw before. And that's
Right.
what this telescope's going to do for us.
Yeah. Speaking of things we haven't really seen before at this kind of resolution, let's look at another image that was released, the Southern Ring Nebula. If we can sort of bring that up. And why don't we continue with you, George, because I think Miri played a pretty critical role in getting this together. So why don't you tell us about this? And then, Marcia, maybe you can give us some NIRCam insights into what we're seeing.
So this is actually the NIRCam image. Maybe Marcia should describe this first. And then we
Yeah.
can
Why don't
go
you
to
start
the
with that,
bridge.
Marcia, first, and we can go. Absolutely.
Okay, so in the center you see a bright star, but it turns out that's not actually the one that died here. You'll see that in the Miri image. What you see around the outer edge is kind of a chocolate colored, very structured filamentary material. And what this is evocative of is how the central star died in a series of convulsions and released kinds of dust that you can see in this orangish, chocolatey-like color. And there are kind of like little tunnels, holes in this structure that lets some light get further out. And another thing that I find very amusing about this picture, which has nothing to do with the planetary nebula, but along the left-hand side, there's something that looks almost like a little scratch. And that's actually a galaxy. And what we're discovering with Webb is that Webb is so sensitive in the sort of 3 microns and longer regime that we're very good at picking up all kinds of galaxies. So all of our pictures are getting photobombed by galaxies.
So that's like an
But-
edge-on galaxy, I gather, right? That like little edge line there. Yeah, amazing.
Yeah.
That's amazing. And can we bring in the Miri version of this, maybe a side by side, I think, was released, and we can sort of see those. And maybe Georgia can tell us what it is that we're seeing differently when we look in the different wavelengths on the right hand versus left hand image.
So the MIRI image highlights these wisps and shells and scallops and so on. And those are heated up aromatic molecules. Those are kind of in between what we normally think of molecules and dust. And actually, they're quite common in automobile exhaust. And they're called aromatic because they don't smell very good. But anyway, they get released when a star like the sun, or a little more massive than the sun, gets too old for the hydrogen to sustain it. It's easiest to give the star personality. It desperately tries to keep itself alive by burning helium, by burning carbon. And there's a stage where all this stuff results in big flows of gas inside the star. It becomes unstable. It starts to oscillate. And each time it oscillates, it throws off a little more material. And so what you see are these shells are the past episodes of material getting thrown off the star. And so by looking at this, you can actually do archaeology on the history of the star, which you can now see is this white dwarf. It's to the left of you, as you look at this image, the slightly fainter star in the center. And the reason you can actually see it with MIRI is it's still buried in some of the dust it threw off. So it's heated up to be brighter for MIRI, relatively speaking, than it is for NIRCam. That's just another illustration of why this wavelength is so neat. But just look at this picture and think that each one of those filaments, each one of those shells, represents a spasm of this dying star until it finally collapsed down to the white dwarf that's the star that's at the center and is heating up the rest of the action here.
And this is a similar fate that presumably our sun is facing, not imminently, but in some 5 billion years or so, right? Is this the similar death throes that we envision?
Yeah, it's first going to blow up to about the size of the Earth's orbit.
Yeah.
And then it will go through these spasms, and then the core will separate from the rest of the star, and the core will become a white dwarf, like the one that's in the center of this nebula. And the rest of the stuff will be in a planetary nebula, just like this one.
So, Renee, Pierre, have you guys done any spectrographic studies as yet of this particular source?
Not of this one.
No.
This one
No,
was
not
only
on this
imaging.
one.
Yeah, was only imaging.
No doubt it'll be coming up. So let's also turn then to another really beautiful image, Stephan's quintet. If we can bring up, I think that for us is image 24. So this, I gather, correct me if I'm wrong, but this is now a composite image from NIRCam, Marcia, and from MIRI. Is that correct? This is putting both data sets together to create this image?
It is, and the NIRCam part is kind of the fuzzy, whitish colored stuff, and the really interesting part with all the structure is mostly from MIRI. But there is one very interesting thing. The left-handmost galaxy, if you zoom in on it, it's actually closer to us than the other four, which are actually at the same distance and interacting with each other. But this foreground one, if you zoom in the NIRCam image, you can actually see some of the individual stars in that galaxy, which is, again, just amazing and a testament to how well the optics are working on Webb.
How far away are they? How far away is the close one and the four that are further away?
40 million. I think the closest one is 40 million light years, and the actual group is close to 300. I think it's 290, something like that.
Right. So it's a huge difference. So it's just coincidence that they project onto the sky in the same location. There's no there's no relation between the left one and the others. Is it unusual though to have even a grouping of four that are so? Is that part of what you're going to try to be figuring out as these images are further analyzed?
Actually, galaxies tend to come in groups or clusters, so it's not that unusual. I think the average size of a group may be even 10 galaxies, so it's not that remarkable. But what is remarkable here is that these galaxies are close enough together that they are starting to merge together, which is a process we think might be very important in the early universe. And so getting to see these in a somewhat closer example may teach us a lot about the physics of how these galaxy blobs come together to make a bigger galaxy.
Yeah, if we go back to the image, if we can bring it back up, maybe you can just point it out. I gather it's in the more or less in the center of the group of four. There's two that are quite close together, and I gather those are the two that are on the verge or post-merger.
Yes, they're the ones that are getting the closest to merging, and you can also see that there's kind of pinkish glow along part of the kind of wispy arms, and that's showing where some star formation is being induced by the gas compression from the galaxies coming together. Mm-hmm.
And if we remove, say, the NIRCam contribution, I gather that then exposes the MIRI contribution more directly. Can we see that? I think that is that image 25 on our list. Yeah. So George, is this the MIRI data without the NIRCam contribution?
Yeah, I mean, looking at this, I think you just have to say, "Wow, this is it, right?" And this explains better than a million words could why the optional extra was such a good thing to buy, because look how different this is. And in fact, if you had stripped these out of the previous image, you would have mostly just seen stars, and it would have just like, I'm sorry, Marcia, it would have looked just like all the previous images rather than something that was, well, it would be sharper. You see the individual stars, but to the untrained eye, it wouldn't look that unique. Whereas you look at this and you say, whoa, what is that? And that's because all these aromatic molecules, again, are being heated up by young stars. And this traces where all the young stars are forming. And in fact, there's this one object over to the right that hardly looks like a galaxy.
Yeah.
It's so busy with forming stars. The object to the left is another galaxy that looked like a kind of normal galaxy, and now you see that it actually is just full of these regions of young stars heating up these aromatic molecules and glowing for us.
So John, were you sold early on MIRI?
Yeah, I had no doubt it was the necessary, supposedly optional add-on, because it was so different. If you just extended the Hubble from what it could do out to 5 microns, which the near-infrared does for us, now that's a factor of 3 in wavelength, and it may be or maybe it not show you very different things. But we knew from the very first moments that we knew that this was a possible instrument, that it would show you something completely different. That objects are just too cool to shine in their own visible light, would just be different. So one thing that's really remarkable about this picture is it's got a quasar in it. It's got a black hole in the top. And George can tell you more about it, how we see it as we do in the mid-infrared, but it's different. So as I guess everybody knows, we have a black hole in the middle of every galaxy, and some of them are active, which means things are falling in and getting compressed and hot, and anyway, sending out jets. So George, what do we see here in this top one that's different from what we knew before?
Yeah, I want to start by saying a whole lot of people saw how neat this optional extra would be. A lot of engineers on the project helped too. So what we see at the top is it may be triggered by this interaction. It's a little hard to figure out how this gets started, but gas has fallen into the influence of the black hole. Of course, a black hole by definition is black, so it doesn't glow. So to make it glow, you've got to have gas fall into it. It orbits it. As it does so, it gets heated to very high temperatures and even emits very profusely in the X-ray. And so this is the way we can find massive black holes. This black hole is something like 100 million times the mass of the sun. So it's a very massive spot in space that's heated up, and in fact, there's spectra that were part of the early release that show some of
But
the.
just so I know where in the image, this is the upper portion, the bright upper region. Is that
It's the thing with diffraction spikes.
got it?
It's nicely isolated by
Yeah, it's beautiful.
yeah.
And so
you can see
spectra
it.
have been taken. You say spectra have been taken of this. Pierre, is there any information you give us on what you learned from taking spectra?
Actually, I think there is one image where you see the spectra, and they are actually from MIRI and NIRSPEC in this case, and with quite spectacular spectra from MIRI. This one, I think George can comment on it. It's quite spectacular.
Yeah, I'd love to hear
Well,
it, George.
So this again covers the wavelength range of MIRI. You can see there's molecular hydrogen that's heated up. A really interesting set of lines are the oxygen line and the neon line. You see the extreme right.
I see it, yeah.
Those have to have very, very hard, deep ultraviolet photons to excite those atoms. And so those tell you that there is what we call an active nucleus in there that can't be excited. Particularly the neon line cannot be excited by stars. And in fact, these lines are going to be used a lot with the Webb telescope to find active black holes that are so buried in dust that you can't find them in the visible or even the near infrared.
I see. That's amazing. And what's the mass of the black hole you said, but I didn't hear it? 100 million?
I think yeah,
Amazing.
about 100 million.
About 100 million. Yeah, go ahead, please go ahead.
No, and I think there is basically the next image corresponds to the NIRSPEC version, where basically this one has been observed also with NIRSPEC.
Yeah, do we have the NIRSPEC image of that?
Yeah, and here it's not presented in the same way, and I think it's quite interesting because we already talked, when we talked with René, we presented two ways of doing spectroscopy with JWST. And actually MIRI and NIRSPEC include another way of doing it. I call it the spectroscopic toolbox. Okay, scientists can just pick the best way to observe their objects. And in this one, what you do is you actually get spectra, but not along a slit or not with everything open, but you can get a small image and you get this clean spectra on basically to get a detailed view, spectroscopic view of the objects. And in this case, what you can do is you can reconstruct images at plenty of colors, plenty of wavelengths. And this is the example. And what you see is that depending at which line, these lines of you're looking at, some of them are going to correspond to ionized hydrogen, some of them to iron, some of them to atomic hydrogen, then molecular hydrogen. And actually, they correspond to different parts of the galaxy. And in this case, actually, to different parts of regions where this black hole and the gas, the impact of a black hole through ejection or even radiation impacts the gas of the galaxy. And you see this different morphology. And from there, you can understand really what happens in the core of this active galaxy.
And just to give the audience, a sense of the technological feat of like NIRSPEC, how many shutters, how many slits do you have, and how many do you control? Can you turn them on and off in order to fine tune what it is that you're actually taking the spectrum of?
Yes, for NIRSPEC, it's the other mode. It's the one we used for the first image, where we have a technology actually developed at the Goddard Space Flight Center, which are tiny micro shutters. So the thing, because remember what René said, NIRSPEC needs to select the object, to pick the right one and just mask everything else. And in this case, what we have is 4 arrays. In total, it's 250,000 almost of some micro shutters. They are not larger than the width of the air. So it's really, really micro shutters. Yeah. And you can command them individually. So basically, you just look at all the image from NIRCam. Okay, Marcia and NIRCam, they always set the stage for NIRSPEC. You take the image, you know where the object is going to fall, and you say, oh, I'm going to open this one, this one, this one. And that's what the observer, the scientist will do. And from there, we get the spectra. So that's the very novel technology, actually, and quite impressive.
Yeah, I think impressive is an understatement. It's a astounding feat. And I think, George, you want to comment on that?
Yeah, I think, as you said, NIRSPEC is
If we can turn now, we have two other images that I want to get to before we conclude our discussion here. I know that John has to leave at 4:30, so I'm mindful of the time. I want to turn to the image that was released having to do with an exoplanet. I mean, one of the questions that humanity has asked since the time we look skyward is whether we are alone, whether there might be other life out there in the cosmos. And the first step in that direction, of course, is to begin to analyze in detail possible atmospheres around exoplanets that have now been in our realm of discovery since the early 2000s. So this particular image is a quite beautiful one. Maybe Renee, I think NIRISS played a key role in this. Can you give us a sense of what we're looking at and what it means?
Yeah, so here we're looking at the spectrum of the atmosphere of a gas giant. In fact, this is a planet about the mass of Saturn, but bigger than Jupiter, because the planet orbits its star in only 3 days, and it's really heated up, and it has a very warm atmosphere. And so this is a transiting exoplanet. So this is a very special class of planets where, from our perspective, the planet goes in front of the star once every orbit. And in fact, when George were having problem to sell MIRI to their project back in the early 2000s, the very first transiting exoplanet was discovered in 2001. At that time, we were not planning to study exoplanet atmosphere. But that's a science team that's imposed itself, and because of the power of probing exoplanet atmosphere. So the game here is actually quite simple, but also very challenging. So we have to measure the dip of this of the light as the planet goes in front of the star, and you do that with spectroscopy with every colors. So if the atmosphere has some molecules like water, for example, well, at that wavelength, that color, the planet will appear slightly bigger. And it's what you see here. And if we see bumps and wiggle that are telltale signature of molecule in the atmosphere. And all these bumps here are water, but in the nearest wavelength range from 0.6 to 2.8 microns, we're sensitive to carbon monoxide and also methane. And that's only one view of the wavelength range, but all four science instruments, NIRCam, NIRSpec, MIRI, can also take their part of the spectrum. So this is a very important science mode with JWST that will allow us to study exoplanet. And of course, we're not just interested in looking at gas giant planets. We're interested to look at much smaller planets, rocky planets that are in the temperate regimes. And we have targets like this. You probably have heard of this famous planetary system, the TRAPPIST-1 system, that has 7 planets orbiting a very small star, not much bigger than Jupiter. And they all transit their star, and 3 of them are right in the habitable zone. And so the big question is there any atmosphere around these planets? And if so, what are they made of? And so that star, that planetary system, all these planets will be observed quite a lot in the first year with all science instruments to try to answer that question. Are there any atmosphere? And if so, what it's made of? That's a very first step to assess the ability, the habitability of these planets.
So this is proof of principle that you can do these kind of incredibly subtle measurements. What other biomarkers would you be looking for? What would be the moment when you say, wow, this is starting to look like it may support the conditions necessary for life?
Well, it is very speculative, but I mean, over the whole wavelength range, I mean, we can detect, we are sensitive to oxygens in the nearest wavelength range, but we know that that would require a lot of observation to detect that. In the MIRI wavelength range, there's ozone, 3 oxygens together, that we could potentially detect that. But we know that this would take a lot of observing time to detect this. But it's we don't really know. And again, the very first question we want to answer, perhaps this first year, I hope, is there any atmosphere around these planets?
Amazing.
And about 25% of all observing time in Webb in first year will be dedicated to exoplanet. a large fraction of which to do exoplanet atmospheres. But there's other modes that we haven't discussed yet, and yet are very powerful. NIRISS, NIRCam, and MIRI have specific modes to do high contrast imaging and the ability to detect very faint companion exoplanet very close to their star. And that's a major science team also that's going to take quite a lot of time in cycle 1, in first year.
I see. Spectacular. In the remaining time, I'd like to turn to the final image, one that folks who are fans of space imagery will know a version of from Hubble, I believe, the Carina Nebula. Can we bring? So this is the Hubble image, and if we had time, I'd poll the audience to see how many people are familiar with it. I suspect it's non-trivial, but it's nice to bring this up first, because now if we transition to the new image, you really wow, right? I mean, again, it's just sort of a startling moment when you see that kind of resolution. I don't know who wants to start us off. Maybe Marcia, do you want to tell us what we're seeing here?
We're seeing, again, a multicolored image, and off the top of the image, where it looks almost like a blue sky, there are some very young hot stars that are emitting so much ultraviolet radiation that their photons are starting to eat into the edge of this surrounding cloud that was basically the birthplace of all these stars. And so this is sometimes called the cliff. But what's very interesting is that when you start zooming in, you will see some areas that are not stars, because they don't have the diffraction spikes. They don't look like little snowflakes, but are sort of this yellowish color. And some of those are regions where a baby star, not yet really a full-fledged star, we call them protostars, have jets coming out that are crashing into the surrounding gas and exciting shock waves that light up in molecular hydrogen. And NIRCam has a filter that is tuned to exactly the wavelength that molecular hydrogen emits. And so we can find these jets, and when we start looking around in here, we see all kinds of funny little structures. It's going to take everyone quite a long time, just from this one image, to parse out all the things that can happen in a star-forming region.
And that's a pure NIRCam data set?
Yeah, this one is.
And there is a version of this, I gather, which also has some MIRI data composited too. Is that this one here? Or is this just, George, can you tell us what we're seeing here?
Yeah, this brings those aromatic molecules to the fore. And so you could see how, it's almost like there's clouds creeping in over the cliffs from the ocean, isn't it? That's not exactly what we're seeing, but that's what it's reminiscent of. And so you're seeing a whole different dimension of what's going on in this complex of interstellar material and forming stars. And I guess I should add, part of the secret of what you're seeing, the last infrared telescope we talked about a little bit, the Spitzer telescope, had one moving part among all of the instruments. And what this discussion is benefiting from is we have very, very sophisticated instruments on JWST in addition to all its other attributes. So this is not just a big telescope, not just a cold telescope, but it's a very sophisticated observatory, and you're seeing all kinds of aspects of these sources that it reveals because of that.
Yeah, no, it's absolutely amazing. So, John, before we wrap up, obviously this is kind of day one, right? This is the starting line. The shotgun has gone off, and now scientists are going to be analyzing this data with great passion, great interest. How is the observing time allotted? I saw a pie chart. I don't even know if we have it. That sort of gave a sense. Yeah, there it is. So was there some committee, I presume, that got together and tried to figure out which project should get which time going forward? How do you make these kind of decisions?
Yeah, we do it with committees. So we announced the opportunity for the entire world to propose. We told them the rules and when everything was due, and what objects had already been claimed. And so please send your proposal. And by the way, write it so we can't tell who you are when we're reading the proposal. This should be called anonymous. So if you're a dog on the internet and you can spell, you can send in your proposal. So what happened actually is it was much more equitable in judging than before, and even got about, I think, 10% of the winners were graduate students. So we're welcoming a great many new investigators because they had good ideas. So
now I noticed
thrilled with
obviously,
that.
yeah, I noticed it obviously is by percent, which is percent of the total viewing time. I gather you got an incredible dividend from the launch being so spectacularly precise that you used up very little fuel to get the telescope into the correct position. So I remember we spoke about this in a program, I guess, I don't know, November or something, and you were hoping for 10 years there, but you said maybe more. Now what's your view? Where do things stand?
Right away we thought, well, we think we got 20 years. And then it turns out we're not spending fuel very quickly, so maybe even more. So I'm keeping our fingers crossed that we are driving our telescope conservatively and cautiously, and fuel economy is good for us.
Wow. So if that's the case, conceivably there are graduate students of the future yet to be born. Is that yeah, right?
That's
Who
true.
may actually be using this machine. Wow.
That's possible.
That's an amazing thing. Well,
So,
it must be incredibly thrilling to see
we're
this
all
going
very
on.
pleased, and the people that you're seeing on the screen besides me all have observing time that they are going to keep on going. The observations will be taking every day, and so we have a full program. Every 5 days we'll have twice as much data as we had yesterday. So. And documentation will be published today, and the images will be available for scientists to analyze tomorrow. And so we are so thrilled to see this happening, and welcome all of the people to look at those pictures and say, look what I found. You didn't even tell me that was there. And so we are thrilled. And so we've done our job as instrument builders and telescope builders, and now it's over to the science world to do what scientists do and take pictures and figure out what they mean.
So before we go on that inspirational note, I'm just wondering, would anybody want to posit a guess, or maybe in your wildest dream, what insight do you hope in your wildest dream that the web will provide? Does anyone have a pet question or a pet goal that may be achieved in the not too distant future?
I mean, I really hope that we can finally settle the arguments about what kind of object was the first kind of galaxy-like thing to form after the Big Bang. There's been lots of theories this way and that way, and I hope we can settle that one for sure.
Yeah,
George,
myself,
any
I'm
thoughts on
looking
that?
forward about.
Renee?
Sorry. Yeah, I'm looking forward about the exoplanet atmospheres and what we're gonna learn, and I suspect there will be some surprises there.
Amazing. And Pierre?
I joined Marcia actually because NIRSpec has been designed really to look for these objects, and finding the spectroscopic signature of a different composition of this first object is something that is a kind of holy grail for a lot of high redshift galaxy aficionados. So yeah, same as Marcia.
Absolutely.
I'm excited.
George, any thought on that?
I want to find where the first of these supermassive black holes came from. We've found quasars at such a high redshift, so close to the beginning, that we're having a lot of trouble explaining how to grow a black hole fast enough to power these quasars. So that's a big mystery.
So John, I'm giving you the final word, and just preface it by saying, you use the COBE satellite to give us insight into the microwave background radiation, giving us insight into the Big Bang itself. What would you dream of happening with?
Oh my goodness! I would hope that we, sort of as an observer, I would hope to find something that we never guessed was even supposed to be there. So, but aside from that, where should we hope to find surprises? we know so little about the actual formation of stars, so little about the actual formation of galaxies and black holes. We have lots and lots of theories. We're getting better computer simulations. But when I ask the computer scientists, well, when are you going to show us what we're going to see before we see it? And they say, we can't. It is too hard. So my expectation is we're going to get surprises every few days that things are not as we thought.
Amazing. Well, I look forward to hearing about those surprises. And again, thank you. Well, number one, congratulations to you and the entire team. Thank you so much for taking the time out to give us some insight into this first release of images. And I think I speak for the whole world as saying it's so exciting to imagine what might be coming down the pike as the James Webb Telescope continues its mission. So thank you all so much for joining us. And to the rest of the audience, let me just quickly note, thank you for being part of this conversation. You should follow the World Science Festival. There's a little button where you can click in to follow us through our newsletter. We have programming both of this sort, but on all manner of science topics under the sun that will be released in the coming weeks and coming months. But yes, today is a real critical moment. The first step in a new view of the cosmos that we imagine the James Webb Telescope will provide us. So the whole world thanks the team, and thank you and the audience for joining us. Signing off from New York, I'm Brian Green.
Thank you, Brian.
Thank you,
Thanks a lot.
Brian.
Thanks.
Bye-bye.
Bye-bye.